The universe has a shape, and for the entire history of human science, we were simply too blind to see it. Until now. James Webb, the most powerful eye humanity has ever pointed at the cosmos, didn't just capture images of deep space, it captured the truth. The actual geometry, large-scale structure, and a hidden web of dark matter nobody knew existed. But the deeper it looked, the more dangerous the data became. Because Nobel Prize-winning scientists measuring how fast this universe expands keep arriving at two different answers that cannot both be true. That is not a small disagreement. That is a crack in the foundation of all modern physics. And what Webb found about the true shape of the universe is exactly where the answer is hiding. Before we dive in, if you love exploring these kinds of deep space videos, a simple like or subscribe really helps this channel reach more curious minds like yours. Now, let everything soften, and together we drift into space. When most people picture the universe, something very specific appears in their minds. Stars, galaxies, enormous distances, a kind of vast, dark emptiness scattered with brilliant points of light, and maybe, somewhere far beyond all of that, an edge. Or perhaps no edge at all. That picture is not wrong, but something crucial is missing from it, and what is missing is not a detail. What is missing is the shape of the container, the geometry of space itself, and the invisible architecture that has decided, across 13 billion years of cosmic time, where every star, every galaxy, every cluster of light has gathered. That architecture is what this story is about. We need to be precise about what we mean by the shape of the universe, because this word does something very specific in physics, and it is not what we usually mean when we use it. When a physicist talks about the shape of the universe, they mean geometry, the geometry of space itself, and geometry turns out to be a surprisingly direct, measurable thing, not a philosophy. Think of it this way. On a flat surface, a sheet of paper, draw a triangle, any triangle, measure its 3 interior angles and add them together. The answer is always exactly 180 degrees. Always. That is what flat geometry does. But now imagine drawing a triangle on the surface of a globe. Start at the North Pole, draw one line straight down to the equator, a second line along the equator, then connect them back up to the pole. Measure those angles. They add up to more than 180 degrees because the surface is curved, curled inward like a sphere, and the rules of geometry behave differently there. Now, imagine the opposite. A surface shaped like a saddle, curving outward in every direction. Draw a triangle there, and the angles add up to less than 180 degrees. Negatively curved. Different geometry entirely. Space itself behaves exactly this way. The universe can be positively curved, finite, like the surface of an enormous sphere, curling back on itself, such that if you travelled far enough in one direction, you would eventually return to where you started, the way a ship sailing west eventually reaches the east. Or it can be negatively curved, open, expanding forever in ways that never loop back. Or it can be flat, following the same clean rules a child learns in a classroom. Parallel lines that never meet, distances that scale exactly as predicted, extending outward without end. Each of these possibilities has completely different consequences for the fate of every galaxy, for whether the universe has a size that could ever, even in principle, be known, for whether the cosmos will expand forever or one day reverse. The shape of the universe is not a philosophical curiosity. It is the most fundamental fact about the place we live, and we found a way to measure it. About 380,000 years after the Big Bang, 13.5 billion years ago, the universe crossed a threshold. Before that moment, the entire cosmos was a plasma so hot and so dense that light could not travel more than a short distance before being absorbed. The universe was opaque, sealed shut, completely dark from the inside. Then the universe cooled just enough for electrons and protons to combine into neutral hydrogen atoms for the first time. And the moment that happened, in cosmic terms, instantaneously, light was set free. A flood of photons released in every direction, streaming outward through suddenly transparent space. That light is still traveling, still here, more than 13 billion years later, stretched by the expansion of the universe into faint microwave radiation that fills the entire sky. We call it the cosmic microwave background, or the CMB, the oldest light in existence, the universe's first photograph. To most instruments, the CMB looks almost perfectly uniform, a faint, nearly identical glow in every direction, its temperature varying by less than 1 part in 100,000 from one patch of sky to another. But embedded within that near-perfect uniformity are precise, subtle fluctuations, patterns pressed into ancient light like a fingerprint, and those patterns encode in remarkable detail the geometry of space itself. Reading them required instruments of extraordinary precision. 2 missions were built for exactly that task. The first was NASA's Wilkinson Microwave Anisotropy Probe, WMAP, launched in 2001. For 9 years, it mapped the CMB with greater resolution than anything before it, producing the first precise all-sky portrait of the early universe. The second was ESA's Planck spacecraft, launched in 2009, more sensitive still, producing a CMB map of extraordinary detail and depth. What both missions found was the same, and it was remarkable. Scientists going into these observations understood what to look for. Certain acoustic features in the ancient light, regions of compressed and rarefied matter frozen into the CMB when the universe was less than 400,000 years old, would appear at a predictable angular size if space were flat, larger than predicted if the universe curved inward like a sphere, smaller if it curved outward like a saddle. The models said flat. The data confirmed it, with stunning precision. The Planck collaboration's final results, published in 2018, confirmed the geometry of the universe is consistent with spatial flatness to within 0.4%. That number deserves a translation. Picture a carpenter's level so perfectly calibrated that it could tile a floor the size of a continent, from one coastline to the other, and detect any deviation in height smaller than the thickness of a single sheet of paper. That level of flatness, applied not to a floor but to the entire fabric of space across the observable universe. Scientists were not entirely surprised, but the precision of the confirmation was deeply satisfying. The universe appeared to be geometrically simple, as flat and clean as the most elegant of the possible answers. For a time, that simplicity felt like resolution. But here is the problem. Geometry is not the whole story. Knowing that space is flat tells us how it behaves mathematically. It says nothing about what is inside it, nothing about how matter arranges itself, nothing about structure. And when scientists began mapping that structure across the full depth of the cosmos, what they found was not simple at all. Pour a glass of water and let it sit perfectly still. The water looks uniform, the same throughout, every part like every other. Now imagine releasing 2 trillion objects into that water, each one pulling gravitationally on every other, across billions of years of time. Where do they go? Not uniformly distributed. They cluster. They stream. They form threads and sheets and enormous hollow spaces between them. That is what the universe looks like. Galaxies, all 2 trillion of them according to estimates by astronomer Christopher Consulis and his team at the University of Nottingham, published in the Astrophysical Journal in 2016, do not float randomly through space. They gather into enormous elongated threads stretching hundreds of millions of light-years across. Those threads intersect at colossal nodes, where galaxy clusters numbering in the thousands pile together at the junctions, and between the threads lie vast, nearly empty regions, cosmic voids, Space is so immense that if our entire Milky Way were placed inside one, the nearest major cluster of galaxies would be so far away that its light would take tens of millions of years to reach us. To give those distances a foothold in something real, if a single light year were compressed to 1 millimeter, a distance you could fit 20 times across the width of your thumbnail, a single one of these filaments would still stretch for more than 100 kilometers, or about 60 miles. These are not small features on the map of the universe. They are the map. Astronomers call this the large-scale structure of the universe. But it has another name, one that captures what it actually looks like from far enough away. The cosmic web. Not a metaphor, a description. At sufficient scale, the universe looks like an immense three-dimensional net of glowing threads, a web of matter stretched across billions of light years, with vast, dark emptiness yawning between its strands. Not a uniform filling of space, a pattern, a structure with a skeleton. Here is the part that deepens everything we have just established. That skeleton is not made of stars. The threads of the cosmic web are not held together by the gravity of the galaxies we can see. They are held together by something that emits no light, absorbs no light, and interacts with nothing we can directly detect. Dark matter. Dark matter is invisible by definition, not because it is distant or dim, but because it simply does not interact with light in any way. Every photon that has ever traveled through a region dense with dark matter passed straight through, as if the dark matter were not there. And yet, its gravitational influence is undeniable. The rotational curves of individual galaxies, the behavior of galaxy clusters, the precise temperature fluctuations in the CMB itself. Every independent line of gravitational evidence points to the same conclusion. Roughly 27% of the total mass-energy content of the universe is made of this invisible substance. To put that in proportion, all the stars, all the gas clouds, all the planets, all the atoms that make up everything we have ever seen or touched or measured represent less than 5% of what actually exists. Dark matter outweighs visible matter by more than 5 to 1, confirmed independently by NASA, the Harvard-Smithsonian Center for Astrophysics, and the European Organization for Nuclear Research. Dark matter is the thread running through everything, the invisible filament that, in the early universe, decided where matter would cluster and where it would not, where the cosmic web strands would form, where the voids would open. Every galaxy we have ever seen gathered first around a concentration of dark matter. The visible universe, every galaxy, every star, every human civilization is the luminous foam that formed on top of an ocean we cannot see. Our theoretical models, built patiently over decades from WMAP and Planck data, from galaxy surveys and computer simulations, describe this web in careful detail. They predicted how early the first filaments should form, how quickly galaxies should accumulate at the dark matter nodes, how massive those early galaxies should be. When they should appear, the predictions were confident. The physics felt settled, and no telescope had ever seen far enough back in time to truly test them. Webb was built precisely to test them. What we had assembled by the time Webb launched was a coherent and genuinely beautiful picture of the universe, a flat geometry confirmed to extraordinary precision, a vast, invisible skeleton of dark matter threading through space, pulling visible matter into the filaments and nodes of the cosmic web, a theoretical timeline, a carefully constructed schedule for when the first galaxies should have assembled out of that dark scaffold, and how large and mature they should be at each stage of cosmic history. The picture was elegant, well supported, and it made specific, testable predictions about the very early universe. Predictions no instrument had ever been powerful enough to check, because no telescope had ever seen far enough back in time to reach that era. Webb was going to change that, and the physics community was confident about what it would find. It found something else entirely. The invisible thread of dark matter running through the cosmos, the structural foundation we believed we understood, had apparently done something in the earliest chapters of the universe that none of the models had predicted. Not wrong by a small margin, wrong in ways that stopped astronomers mid-calculation and forced a more fundamental question. Was it the data that was surprising, or were the foundations of our model more fragile than we had thought? What Webb showed, in the very first deep images it returned, were galaxies that had no business existing when they did. Galaxies too large, too structured, too fully formed, present at a moment in cosmic history when the universe should have been little more than a thin, cooling haze of hydrogen just beginning to stir. How does a universe build its structure before the rules say it should? That was the question Webb had just placed in the hands of every cosmologist on Earth, and it was only the first of many. A patch of sky smaller than a grain of sand held at arm's length. That was all they pointed it at. That was the opening bid. What came back was not what anyone expected, not in scale, not in depth, and not in what it said about when the universe decided to grow up. For decades, astronomers had been working with a kind of educated guess about the early universe. Not a wild guess, a careful, well-reasoned one, built from decades of observation, tested against every deep sky survey we had ever conducted. The guess was this: the early universe was raw, chaotic, and simple. Galaxies in their infancy would be small, disorganized, scattered fragments of star-forming gas that had barely begun to collapse under gravity, like seeds that had just been planted, not trees. And we believed this deeply, confidently, because every telescope we had ever built pointed at the deepest sky seemed to confirm it. Galaxies in the distant past looked young, irregular, primitive. The further back we looked, the simpler things became. The picture held, the physics agreed, the models aligned. But no telescope had ever seen far enough back to test the very beginning. And then we built one that could. The James Webb Space Telescope is not a replacement for the Hubble Space Telescope. Understanding what it actually is and what it was built to do is essential to understanding why what it found was so extraordinary. Hubble sees invisible light, the same light our eyes use, and visible light, for all its power, carries a fundamental limitation when you try to look into the deep past. The universe has been expanding since the moment it was born, and that expansion does something to light as it travels. It stretches it. The way a note from a passing train drops lower as it recedes, the wavelength of ancient light grows longer and longer as the universe carries it across billions of years of expanding space. By the time that light reaches us, it has been pulled far, beyond what our eyes, or Hubble's cameras, can detect. The original visible and ultraviolet light from the very first galaxies arrives at Earth not as visible light at all. It arrives as infrared, as heat radiation, as a form of light entirely invisible to any visible light telescope. Webb was built to see infrared. That single design choice transforms the telescope from a very powerful camera into something closer to a time machine. To do this well, Webb needed a mirror large enough to catch the extraordinarily faint signals arriving from 13 billion light years away. Its primary mirror spans 6.5 meters across, 21 feet, assembled from 18 hexagonal segments coated in a thin layer of gold, a material chosen specifically for its infrared reflectivity. Together, those 18 segments gather a light collecting area of 25 square meters, roughly 270 square feet. To grasp what that means, Hubble's mirror has a collecting area of about 4 square meters. Webb collects more than 6 times as much light. The difference is not just a matter of seeing things more clearly. 6 times the light gathering capability means Webb can see objects so faint, so remote, that Hubble could not detect them even in principle, regardless of how long it stared. And Webb has to be cold. Deeply, extraordinarily cold. Infrared radiation is essentially heat. If the telescope's own mechanical warmth contaminated the signals it was trying to detect, it would be like trying to listen for a whisper inside a thunderstorm. So Webb orbits a point in space about 1.5 million kilometers, roughly 900,000 miles, from Earth, always behind our planet, always shielded from the sun by a 5-layer sunscreen the size of a tennis court. At that distance, maintained at a temperature of around minus 233 degrees Celsius, colder than the surface of Pluto, the telescope can hear its whispers. Webb launched on Christmas Day, 2021, folded like an intricate piece of origami inside an Ariane 5 rocket. For the following 6 months, as it travelled to its orbital position, and its 18 mirror segments were painstakingly aligned with a precision of 1/10,000th the width of a human hair, the astronomical community waited. On July 11th, 2022, the wait ended. In a live event at the White House, NASA unveiled the first full-colour image from Webb. The target was a galaxy cluster called SMACS0723, a massive congregation of hundreds of galaxies some 4.5 billion light-years away. But the cluster itself was almost incidental. What mattered was what the cluster's gravity did. It acted as a natural magnifying glass, a gravitational lens, bending and amplifying the light from thousands of vastly more distant galaxies behind it, stretching some of them into long, curved arcs of light and bringing others into sharp focus that would otherwise have been completely undetectable. The exposure time was 12.5 hours. 12.5 hours, and Webb reached depths that the Hubble Space Telescope had never achieved in years of staring at the same empty sky. The patch of sky covered in that image, the entire field of view, was about the size of a grain of sand held at arm's length by someone standing on the ground. One grain of sand, and inside it, thousands of galaxies. The farthest light in that image had travelled for 13.1 billion years before striking Webb's mirror. 13.1 billion years. The universe itself is only 13.8 billion years old. Webb was staring at light that left its source when the cosmos was less than 700 million years old. You are sitting wherever you are right now, watching this, breathing normally, and in that single image there was a galaxy whose light was already ancient before the sun was born. To understand why Webb could see what Hubble could not, we need to sit with the redshift idea for just a moment. Picture a wave moving across water. Now imagine the body of water itself is expanding as the wave travels. The wave stretches, its crests and troughs grow further apart. By the time it reaches you, it is a completely different wave than when it started. Light behaves exactly this way in an expanding universe. A galaxy 13 billion light-years away emitted its light as ordinary visible and ultraviolet radiation when its stars were young and hot. But in the 13 billion years that light spent crossing an expanding universe, space itself stretched that light. The wavelengths grew longer and longer. By the time they reached us, they had been pulled completely out of the visible spectrum, shifted all the way into the infrared. No visible light telescope would ever see them. They are invisible to human eyes, invisible to Hubble, invisible to every ground-based observatory. On Earth, only an infrared observatory looking from cold, still space could catch them. Webb does not just see further than Hubble. Webb sees a completely different kind of information, the stretched, cooled, ancient light of a universe that human eyes were never built to detect. The first deep field was a demonstration. One target, one stare, a proof of capability. The Cosmos Webb survey was something altogether different. Cosmos Webb is the largest single observing program Webb conducted in its entire first year of science operations, led by astronomers Caitlin Casey of the University of Texas at Austin and Jehan Kartal-Tepe of the Rochester Institute of Technology. Along with a collaboration of nearly 100 scientists from around the world, the survey set out to do something ambitious and specific: map a wide slice of the deep universe systematically, building not just snapshots of individual objects, but a coherent picture of cosmic structure across billions of years of time. Over 255 hours of observing time, Webb mapped a region of sky spanning roughly half a square degree, an area about equal to the face of 3 full moons side by side. That does not sound large, but the depth to which Webb could see within that area was staggering. Picture someone taking a long, thin core sample from deep in the Earth, not digging across a wide area, but drilling straight down through billions of years of geological history, layer after layer, all the way to bedrock. Cosmos Webb did the same thing with time, drilling vertically through the history of the universe from galaxies that exist today, all the way back to galaxies that formed when the cosmos was less than 1 billion years old. When astronomers began analysing the full data set, released publicly in 2025 as the Cosmos 2025 catalogue, the number of galaxies contained in that single half-square degree survey came to nearly 800,000. Let that land. 800,000 galaxies in a region of sky the size of 3 full moons, each one a collection of billions of stars, some of them with planets, some with the chemistry that makes life possible, all of them invisible to every instrument that came before Webb. But something else came with that number, and it was not comfortable. The standard cosmological model, the framework astronomers had spent decades constructing and testing, made specific, concrete predictions about what that survey should contain. Based on our understanding of how matter clusters under gravity, how dark matter scaffolding organizes itself over time, how quickly star formation should proceed in the early universe, the models projected a clear picture. They expected to find early galaxies at high redshifts, genuinely early, genuinely ancient, but small ones, compact, low mass. The early universe, the models said, had not yet had time to build anything massive. The cosmic web was still forming. The dark matter halos were still pulling matter in. Structure takes time to grow. Scientists were confident. The entire theoretical framework of modern cosmology predicted it, and every prior telescope had never been able to see far enough back to test the earliest chapters. So the predictions had never truly been challenged. Then the data came in. Among the nearly 800,000 galaxies that Cosmos Webb catalogued, and in Webb's subsequent targeted deep observations in programs like JDAS, the JWST Advanced Deep Extragalactic Survey, astronomers began finding galaxies that did not behave as the models predicted. Not young, small, fragmentary galaxies struggling to form their first stars, but old-looking galaxies, massive galaxies, galaxies with structured morphologies, organized disks, developing spirals, established stellar populations, at distances and redshifts that placed them within the first few 100 million years after the Big Bang. In the first light image alone, spectroscopic analysis identified a galaxy whose light had been traveling for 13.1 billion years, emitted when the universe was less than 700 million years old. Not a fragment, an established structure. In the JD's program, Webb confirmed galaxy JD's GSZ 13-0, existing just 325 million years after the Big Bang. 325 million years. At that point in cosmic history, according to the standard model, the universe should have been little more than a spreading fog of hydrogen, with the faintest gravitational seeds just beginning to stir. What astronomers found instead was a galaxy that had already assembled itself, already begun forming stars, already carved structure out of the darkness. And that was only the beginning of what the data contained. Across the astronomical community, a careful and measured pushback against the standard timeline models began forming. Not a crisis, not a collapse of the science, but a genuine growing tension between what the data showed and what the physics had predicted. Some astronomers argued for patience. Perhaps the observations had uncertainties. Perhaps some of the earliest galaxies were not as massive as they appeared. Perhaps dust or unusual star formation histories, or limitations in how we inferred their masses from light alone were distorting the picture. The science of measuring a galaxy's mass from its infrared brightness is not straightforward, and early estimates can carry significant error. Others argued that the tension was real and that the standard timeline, the ΛCDM model, was simply missing something fundamental about how structure forms in the earliest universe, something that allowed gravity, or dark matter, or some process not yet accounted for, to build complexity faster than any of the models had projected. Neither side had resolved the question. What everyone agreed on was this: Webb was revealing an early universe that was more complex, more structured, and more surprising than the best models in existence had predicted. Not slightly more, dramatically more. The survey data was only beginning to be processed. The full Cosmos 2025 catalogue, nearly 800,000 galaxies, the largest and deepest survey of its kind ever assembled from a single telescope, was now in the hands of astronomers around the world, being analysed by research teams from dozens of institutions. And with every new analysis, the same unsettling pattern kept emerging. The early universe had not developed slowly. Something in the very first chapters of cosmic time had allowed galaxies, enormous, organised, star-filled systems, to exist far earlier than any model had predicted. But here is what made that truly strange. Galaxies are not built from nothing. They require scaffolding, a gravitational architecture that guides matter into the right places at the right time. That architecture, as we established, is the invisible dark matter web. And if galaxies were forming faster and more massively than expected, it meant the dark matter web itself, the cosmic skeleton, had to have been more structured, more developed, more organized in the early universe than our models allowed. The question that was emerging from the data was not simply when the first galaxies formed. It was what, exactly, allowed them to form so quickly, so massively, so soon after a universe that had barely cooled. And whether the answer lay in dark matter, in black holes, in some physics we had not yet understood. That was the question now pressing against every model, every simulation, every assumption the cosmological community had built its picture of the universe upon. The answer, it turned out, was stranger than the question. Ivo Laber was staring at a tiny red dot on his screen and running the same analysis for the third time. The number kept coming back wrong. Not slightly wrong. Wrong in a way that made him think he had made a mistake. He hadn't. He had just found something the universe was not supposed to have built yet. When scientists use the word impossible, they are rarely being dramatic. They are trained to hedge, to qualify, to allow for measurement error, observational bias, software glitches, and the dozen other mundane explanations that tend to diffuse a surprising result. Scientists do not like impossible. Impossible keeps you up at night. Impossible means the framework you've spent decades building has a crack in it somewhere, and you don't yet know where. In the summer of 2022, just weeks after Webb's first images were released to the world, the impossible began to appear. Not once, not twice. Within days, it had multiplied into 6, and it has not stopped multiplying since. To understand why what Webb found was so disorienting, we need to understand what astronomers were expecting to find, and why that expectation was so well reasoned, so carefully built, that it had every right to feel settled. The standard model of cosmology, built from decades of observation, tested against thousands of data points, refined through missions like Hubble and Planck and WMAP, made a very specific prediction about the early universe. It said this: in the first few 100 million years after the Big Bang, the universe was too young, too diffuse, too newly structured for large galaxies to exist. The dark matter web was still in its infancy. Gravitational seeds were still pulling scattered gas together. Star formation was just beginning. The first galaxies, this model insisted, would be small, clumpy, irregular. Compact fragments of matter that had barely begun to coalesce. Picture a city being built from scratch. In the first month, you don't see skyscrapers. You see foundations being poured, scaffolding being raised, raw materials arriving at a construction site. The idea that a fully finished, fully inhabited skyscraper could already be standing on day 30, built, occupied, and operational, would violate everything you know about how long construction takes. That is precisely the logic behind the standard predictions for early galaxies. Galaxies grow from seeds. Seeds take time, and the universe, in its first few 100 million years, had almost no time at all. According to this model, any galaxy visible from that early era should be between 10 and 100 times smaller than a galaxy like our own Milky Way. Not a finished city, a few scattered buildings at most. Scientists were confident. The physics was clear, the models agreed they were wrong. It was July 2022. Ivo Laber, an astrophysicist at Swinburne University of Technology in Australia, and his colleague Erica Nelson at the University of Colorado were examining the very first scientific images from Webb, barely a week after they were publicly released. Within that initial data set, Laber noticed something in a tiny red point of light that his analysis software was returning an unusual number 4, mass. More mass than should have been possible. He ran the analysis again. The same result. He ran it a third time. The software was telling him that this small red dot represented a galaxy containing the mass equivalent of roughly 100 billion times the mass of our Sun. 100 billion solar masses, comparable to the total stellar mass of the entire Milky Way galaxy. And it existed when the universe was only about 700 million years old. Less than 5% of its current age. He checked again. Then he found 5 more objects with similar properties in the same data set. "I nearly spit out my coffee," Laber later wrote. "We just discovered the impossible. Impossibly early, impossibly massive. Galaxies." The findings were published in February 2023 in Nature, one of the most prestigious scientific journals in the world. Led by Labe and co-authored by a team from Penn State, Yale, the University of Colorado, and several other institutions, the paper described 6 candidate galaxies observed between 500 and 700 million years after the Big Bang. Each appeared to contain far more stellar mass than anything the standard model had predicted would exist at that time. Joel Leger, an astrophysicist at Penn State who worked on the analysis, said something that stayed with the scientific community. Even if half the sample proved wrong, he noted, the amount of mass discovered at that period of cosmic history was up to 100 times greater than anyone had previously thought. Cut the sample in half, and the conclusion barely changes. Let us make certain the scale of this lands properly, because the numbers matter here in a way that is genuinely difficult to absorb. The Milky Way, our home galaxy, the system containing the Sun and all its planets and every star you have ever seen in the night sky, took the better part of 13 billion years to assemble its current mass of roughly 60 billion solar masses worth of stars. 13 billion years. The full lifetime of the universe, more or less, went into building what we live in. One of the galaxies Laber's team found appears to have assembled a comparable mass in just 700 million years. That means it grew at approximately 20 times the rate of the Milky Way. Think of it this way. If the Milky Way is a person who spent a full lifetime, 70 years, slowly building a house brick by brick, then this early galaxy built the same house in under 4 years. But this is where the physics becomes actively disturbing. For a galaxy to grow that quickly, to accumulate that much stellar mass in that shorter time, it would need to do something our standard understanding of galaxy formation says is essentially impossible. It would need to convert nearly 100% of its available hydrogen gas directly into stars. Every atom of gas that fell into its gravitational potential turned immediately into stellar fuel, with almost no waste and no delay. Mike Boylan-Colchin, an associate professor of astronomy at the University of Texas at Austin, who published a separate analysis of these galaxies in Nature Astronomy, stated the problem precisely. We typically observe a maximum of about 10% of available gas being converted into stars in a galaxy. 10%. The laws of star formation, the The competing pressures of gravity and radiation and turbulence build in this inefficiency. The universe wastes 90% of the raw material it starts with. For these early massive galaxies to exist when and where Webb found them, they would have needed to waste almost nothing, 100% conversion, every molecule of gas becoming a star. Not slightly beyond what the models allow, at the absolute theoretical edge of what physics permits, and possibly past it. And then the next galaxy arrived. And the next. In 2024, the JWST team, the JWST Advanced Deep Extragalactic Survey, led by researchers from the University of California, Santa Cruz and the University of Arizona, and co-led by astronomer Brant Robertson, announced the confirmation of the most distant galaxy ever spectroscopically verified, a galaxy now known as JWST 14-0. It existed 290 million years after the Big Bang. 290 million years. The universe today is 13.8 billion years old. 290 million years is roughly 2% of that. At that moment in cosmic time, the universe was a 2% solution. Barely cooled, barely structured, its first stars only recently born. And yet JWST 14-0 spans over 1,600 light-years across. 1,600 light-years, meaning if you placed one end of this galaxy at our Sun, the other end would extend more than halfway to the nearest major star cluster, visible to the naked eye. This is not a fragment, not a seed, not a proto-galactic cloud of gas looking for a direction to collapse. This is a structured, luminous stellar system, bright enough that it immediately puzzled the scientists who first noticed it in their data. Kevin Hainline, an astronomer at the Steward Observatory of the University of Arizona and one of the lead researchers on the discovery, later said that when the spectroscopic data came in and confirmed the distance, he laughed. He had to get up from his office chair and walk down the hallway just to look at the faces of his colleagues. "I was skeptical that it was anything special for a number of reasons," he said. "It just seemed too big and too bright." But the data held. George Rieker, a senior astronomer at the University of Arizona who helped guide the design of Webb's near-infrared camera, said afterward, "Nobody dreamed that there would be galaxies this bright at this high redshift. But the most unsettling detail about JWST 14-0 was not its mass or its brightness. When astronomers analyzed the spectrum of JWST 14-0 in detail, they detected something that had no business being there. Oxygen. Oxygen is not a primordial element. The Big Bang produced hydrogen and helium almost exclusively. Everything heavier than those two elements, carbon, nitrogen, oxygen, iron, all the elements that make planets and organisms possible, had to be forged inside stars. And the only way oxygen gets spread into the surrounding gas of a galaxy is through the deaths of massive stars. When those stars explode in supernovae at the ends of their short lives, they scatter their enriched contents outward, seeding the surrounding medium with heavier elements. For oxygen to be present in a galaxy at 290 million years after the Big Bang, an entire generation of massive stars, possibly more than one, had to have already lived their full lives and died. They had to have been born, burned through their fuel, and exploded, all within an already formed galaxy, at a moment in cosmic history when the universe was barely old enough for those stars to have existed at all. Picture a forest ranger arriving at a newly established national park on its official opening day and finding a 1,000-year-old oak tree already standing there, fully grown, with rings in its trunk proving its age. The tree should not be there. The park was not there 1,000 years ago, and yet the rings are real. That is what oxygen in JWST 14-0 represents. Chemical evidence of a history that the timeline says could not have happened. Detected not by Webb alone, but confirmed in 2025 by the Atacama Large Millimeter Array, ALMA, in Chile, one of the most powerful radio observatories on Earth. The detection is real. The oxygen is there. The JD's team stated it plainly in their report. The presence of oxygen so early suggests that multiple generations of very massive stars had already lived their lives before this galaxy was observed. Multiple generations. At 290 million years after the Big Bang. The ΛCDM model, lambda for dark energy, CDM for cold dark matter, is not a rough guess. It is one of the most precisely tested frameworks in the history of science, calibrated against the cosmic microwave background, against the distribution of galaxies across billions of light years, against the expansion rate of the universe measured in multiple independent ways. For decades, it predicted everything we observed with extraordinary accuracy. The model says that structure builds from the bottom up. Small dark matter halos form first. They gradually merge. Larger halos accumulate around them. Gas falls in. Stars begin to form. Galaxies grow. Everything happens in order, hierarchically, governed by gravity and time. The architecture of the cosmic web was built slowly, layer by layer, the way a cathedral is built, stone by stone, over centuries. But here is the problem Webb has placed at the center of that framework. The most massive, most structured galaxies it has found in the very earliest observations are not small. They are not young-looking, they are not fragmentary, they look finished, as if someone had accelerated the construction of the cathedral to a speed that violated everything we know about how long stone takes to set. The cosmological community is not unanimous on how severe this tension is, and that division is genuine and important. It is not a political disagreement, but a scientific one, rooted in real uncertainties in how we measure extremely distant objects. Some researchers argue that many of the apparently massive early galaxies may have been overestimated. At extreme distances, the technique of inferring a galaxy's mass from the brightness of its infrared light carries significant uncertainty. Dust surrounding the galaxy can make it appear redder, and therefore apparently more distant, than it truly is. Supermassive black holes at the centers of some early galaxies can produce intense radiation that mimics the light signature of large stellar populations, making the galaxy look more massive than its stars alone would justify. Researchers at Johns Hopkins University, in a paper published in Physical Review Letters in 2024, found that accounting for smaller galaxy populations, the standard cosmological model was not necessarily broken by the JWST data. Others maintain that even after correcting for every known source of systematic error, and Webb's spectroscopic confirmations leave far less room for error than earlier photometric estimates, too many galaxies remain too massive, too structured, too chemically evolved for the standard framework to accommodate them without significant modification. A paper published in Nature in 2024 by an international team, led by the University of Geneva, found 3 confirmed, spectroscopically verified, ultramassive galaxies within the first billion years, galaxies with star formation efficiencies suggesting something in the early universe was fundamentally accelerating the process by which gas became stars. Both sides acknowledge the same underlying data. The disagreement is about what that data means, and science at its best looks exactly like this: a genuine, unresolved tension between observation and theory being worked through carefully, measurement by measurement, until the evidence forces a verdict. What is not in dispute is this: Webb is revealing early galaxies that are more numerous, more massive, and more chemically evolved than any model predicted. Not slightly, substantially. The universe built structure where the model said it should not have existed yet. Galaxies assembled in a time frame the physics of gradual accumulation cannot easily explain. Multiple stellar generations lived and died at a moment when the universe had barely begun, and if the galaxy formation timeline is more compressed than the standard model allows, if the dark matter web was somehow structuring itself faster, pulling matter together more efficiently in the earliest chapters of cosmic history, then a deeper question follows. What caused that acceleration? Because the dark matter web we described earlier, the invisible skeleton that pulls galaxies into their places along filaments and nodes, grows according to rules built into the ΛCDM model. Those rules set the pace. They determine how quickly dark matter halos can accumulate enough mass to seed a galaxy. They set the schedule. But if the galaxies are arriving early, ahead of schedule, then something was disrupting or supplementing or entirely circumventing that schedule, and one candidate had been waiting in the dark long before Webb ever opened its golden eye. Something that operates at the very foundation of cosmic structure, deeper than dark matter, earlier than the first stars, something that may have seeded everything. Billions of dark matter particles are passing through your body right now. Through the chair beneath you, through the floor, through the walls. They pass through everything without slowing, without leaving a trace. We know this, and until recently that was the whole truth we had about where they were. We knew they existed. We had never seen them arranged. We have spent the last 3 chapters building a picture of an early universe that defied its own predictions. Galaxies that grew too fast in too little time, with chemistry that accumulated impossibly quickly. Each of those problems pointed toward the same underlying question. What was the architecture that made all of this possible? The dark matter web. That was the answer the models kept returning to, the invisible skeleton threading through the cosmos, the gravitational scaffolding that, in theory, guided everything visible into the places and shapes it needed to occupy. But theory is not observation. A skeleton you cannot see is a claim, not a confirmation. And for decades, the maps we had of dark matter's actual arrangement were blurry, incomplete, and shallow, enough to confirm the broad outlines but not enough to see the detail, not enough to trace the threads between the nodes, not enough to watch the web being assembled across billions of years of time. That changed in January 2026. Before we can understand what Webb revealed, we need to sit with the structure itself, because the large-scale architecture of the universe is one of those ideas that, once you fully grasp it, permanently changes how you see the night sky. On the very largest scales, far beyond individual galaxies, far beyond even galaxy clusters, the universe is not uniform. Matter does not fill space like air fills a room, evenly distributed in every direction. Matter is gathered into a pattern. Picture a spider's web after a morning rain, stretched across a corner of a garden. Not the tight geometric spiral you might imagine in a cartoon, but the kind you actually encounter, irregular, 3-dimensional, with thick anchor strands connecting to heavy droplet-laden nodes, and finer threads stretching between them through open air. And in between the threads, not randomness, but organized emptiness, space that the web deliberately surrounds. Now scale that image to the observable universe. The thick strands are filaments, enormous rivers of gas, dark matter, and galaxies that stretch for hundreds of millions, sometimes over 1 billion light years. The heavy nodes where threads intersect are galaxy clusters, some containing thousands of individual galaxies bound gravitationally together, representing the densest concentrations of matter in the known universe. And the open spaces between the threads are cosmic voids, vast, nearly empty regions that can span anywhere from 30 to 300 million light-years across, volumes of space so large that if our entire Milky Way were placed inside one, the nearest major filament would require light millions of years to reach us. Cosmological simulations and galaxy surveys conducted over decades, from the Sloan Digital Sky Survey to large ground-based programs, had mapped the visible portion of this structure, the galaxies and galaxy clusters that trace the web like lit windows on a dark night, hinting at the geometry of the building around them. And those surveys found the pattern consistent across billions of light years. Everywhere astronomers looked deeply enough, the same web emerged. Not a coincidence, not a statistical fluctuation, a genuine structural property of space itself. But the galaxies are not the web. They are only its markers. The actual body of the web, the thread that holds everything in place, that acts as the gravitational channel guiding gas and matter from the voids into the filaments and from the filaments into the nodes, is dark matter. And for the longest time, that thread had never been mapped in full, only inferred. Mapping dark matter presents a problem that should be, strictly speaking, impossible. The substance emits nothing, absorbs nothing, reflects nothing. No telescope sensitive to any wavelength of light can detect it directly. Point any instrument at a region full of dark matter and see only what the dark matter is not, the galaxies and gas that surround it. The only tool available is gravity itself. When a massive concentration of dark matter sits between a distant galaxy and a telescope on Earth, its gravity warps the fabric of space around it. Light from the distant galaxy, traveling through that warped space, bends. The galaxy's image arrives at the telescope slightly distorted, not just magnified or brightened, but subtly stretched, sheared, tilted. Like the reflection of a ceiling lamp in a shallow bowl of still water, gently pulled out of shape by the curve beneath it. This effect is called gravitational lensing. In its strongest version, when the mass is extremely concentrated, it produces unmistakable arcs and rings of light, the distant galaxy smeared into a glowing curve around the foreground mass. Astronomers call this strong lensing, but dark matter's distribution across the cosmic web is not, in most places, that extreme. Most of the invisible material lies spread across filaments and sheets, diffuse and extended, producing only the subtler version, called weak gravitational lensing. Just a tiny, almost imperceptible distortion of each distant galaxy's apparent shape, an elongation of a fraction of a percent, a tilt that no human eye could detect in any single image. To map dark matter through weak lensing, you need to measure those fractional distortions across thousands, ideally hundreds of thousands, of individual galaxies simultaneously. And to do that accurately, you need to see each galaxy's shape with extraordinary clarity. The slightest blurring, the smallest smear introduced by your optics or your atmosphere, and the signal drowns in noise. Ground-based telescopes could resolve the shapes of roughly 20 galaxies per square arc minute, per tiny patch of sky, before the atmosphere blurred the rest. The Hubble Space Telescope, operating above the atmosphere, improved that to about 71 galaxies per square arc minute. That was Hubble's best, achieved over decades of careful observation. Webb resolves approximately 129 galaxies per square arc minute, nearly twice what Hubble could achieve. And because its mirror is so much larger, because it collects so much more light, it finds those galaxies at greater distances, seeing further back in time, sampling the lensing effects across a far deeper column of cosmic history. The Hubble Space Telescope produced its first dark matter map of the cosmos field, a well-studied patch of sky in the constellation Sextans, in 2007. That map represented roughly 1,000 hours of Hubble observation. At the time, it was extraordinary, the first real portrait of dark matter's arrangement over a broad area of deep sky. Scientists could see the rough outlines, clusters, hints of filaments, the suggestion of a web. But it was a photograph taken through frosted glass. You could make out the shapes. You could not read the detail. Scientists were confident that a clearer image would eventually come. Webb would change the picture, they expected. They were right, in ways that went beyond what most of them had anticipated. In January 2026, a team led by Gavin Leroy of Durham University, Jacqueline McCleary of Northeastern University, and Richard Massey, also of Durham, and a scientist who had worked on that original 2007 Hubble map, published a new dark matter map of the same cosmos region in the journal Nature Astronomy. The map was built from Webb's Cosmos Web Survey data, 255 hours of infrared observation, covering an area about 2.5 times the size of the full moon, containing nearly 800,000 galaxies. The resolution was more than twice as sharp as the Hubble map from the same region. Twice. And the improvement was immediately visible in a way that required no specialist to understand. The side-by-side comparison of the two maps showed, in the Hubble image, soft and blurry concentrations. In the Webb image, those same concentrations resolved into crisp, detailed peaks. Filaments that had been barely suggested in the Hubble data became clear, defined threads connecting the nodes. Galaxy groups too faint and too distant for Hubble to identify appeared in the Webb map for the first time. Small but real concentrations of dark matter and ordinary matter, hundreds of millions of light years away, now visible. Not slightly better, dramatically better. Massey described the moment when he first saw the Webb map placed next to his original Hubble work from 19 years earlier. At a collaboration meeting in May 2025, when a preliminary version of the Webb map appeared on screen beside the 2007 Hubble map, the scientists in the room began to applaud. Not polite applause, he noted, but recognition. The same cosmic structures that had been blurry impressions for 2 decades were now resolved into their true form. Finer filaments, sharper cluster peaks, and structures that had been hiding at the edges of detectability for all that time. What the map revealed, in its clearest and most powerful terms, was a confirmation and a deepening of something we had long suspected, but never seen this clearly. Everywhere the map showed dense concentrations of dark matter. The distribution of ordinary matter, galaxies, gas, stars, followed exactly. Not approximately, not with a broad correlation, with a precision that left no room for coincidence. Richard Massey described it in words that carry a weight beyond their simplicity. Wherever we see a big cluster of thousands of galaxies, he said, we see an equally massive amount of dark matter in the same place. And when we see a thin string of ordinary matter connecting 2 of those clusters, we see a string of dark matter there as well. It is not just that they have the same shapes. The map shows that dark matter and regular matter have always been in the same place. They grew up together. That phrase, grew up together, holds an extraordinary amount of meaning. The standard cosmological model had always predicted that dark matter was first, that the invisible web formed before any star was born, before any galaxy was assembled. That ordinary matter fell into the gravitational trenches already carved by dark matter, the way a river does not cut its own valley from scratch, but follows a geography that was shaped long before it arrived. The cosmic web was the geography. The galaxies were the river. What the Webb dark matter map showed by comparing dark matter distribution across the cosmos field at different distances, and therefore at different epochs in cosmic time, is that this coevolution is real, and it is consistent across billions of years of cosmic history. The dark matter scaffolding and the ordinary matter it gathered have tracked each other faithfully from the earliest observable periods to the present. Every cluster of galaxies Webb found embedded in the map was sitting at the center of a corresponding dark matter concentration. Every thin strand of galaxies connecting 2 clusters had a strand of dark matter threaded through it. The thread that carries the universe, the invisible thread, runs through everything we can see. Here is why this matters, for the question at the heart of everything we have been building. The dark matter web does not just passively sit beneath the structure of the visible universe. It is the mechanism by which galaxies are fed. Filaments are not simply decorative connections between nodes. They function as pipelines, conduits through which gas, drawn by gravity, flows from the emptier voids into the denser filaments, and from the filaments down into the galaxy clusters at the nodes. As gas travels along these filaments, it cools, compresses, and eventually collapses into the dense knots where star formation begins. A galaxy is not a self-contained system. It is a destination at the end of a river system, fed by dark matter rivers stretching across hundreds of millions of light years. This understanding reframes the impossible early galaxy problem in a specific way. If galaxies in the early universe were forming faster and growing more massive than the standard model predicted, one explanation involves the filaments themselves. The possibility that, in the very early universe, those dark matter rivers were running faster, carrying more mass per unit time toward their nodes than any simulation had accounted for. The conditions of the early cosmos, higher density, shorter distances between structures, stronger gravitational gradients, may have meant that the feeding process was more efficient, more concentrated, and more rapid than the models assumed. The Webb dark matter map does not resolve this question, but it provides the clearest structural picture ever assembled of how dark matter organizes itself, and therefore the clearest window yet into what happens when that organization is in place and galaxies begin to form around it. Jacqueline McCleary, who co-led the research at Northeastern University, described the map as a high-resolution picture of the scaffolding of this little corner of the universe. What that phrase points toward is something that will take years to fully investigate. That the corner of the universe Webb has now mapped in such detail is not only the clearest image of dark matter ever assembled, but a testing ground for every question we have raised about early structure, early galaxies, and the speed at which complexity emerged from the simplest possible beginning. Pull back far enough from the dark matter map, and a particular quality of the universe's structure comes into focus that no description quite prepares you for. The vast majority of the universe's volume, the overwhelming bulk of the space within the observable cosmos, is void, empty. The filaments and walls and nodes that constitute the cosmic web, for all their enormous scale, occupy only a thin fraction of the total volume. The universe, seen from the outside, would look less like a solid object and more like foam, a lattice of thin walls and threads enclosing enormous bubbles of near emptiness, the voids yawning open across tens to hundreds of millions of light years. The cosmic web is not a dense net, it is the skeleton of an overwhelmingly hollow structure, and sitting in that hollow structure, at the nodes, at the intersections of the brightest filaments, are the most massive objects in the observable universe. Galaxy clusters containing thousands of individual galaxies, embedded in halos of dark matter, holding trillions of solar masses of invisible material, linked to their neighbors by the dark threads Webb has now mapped in their finest detail yet. Every galaxy in that map, all 800,000 of them, plus the vast majority that remain too faint and too distant even for Webb, sits embedded in this web. Every star in every one of those galaxies was assembled from gas that travelled down a dark matter filament to reach the place where it was born. And every atom in every one of those stars, including the atoms in your body right now, was forged in one of those stars, scattered by its death, and carried through the web to the particular node and filament where a later generation of stars would form our sun and everything around it. The invisible thread runs through you. The map was a triumph. The resolution it achieved, the structures it revealed, the confirmation of dark matter's coevolution with ordinary matter across billions of years, all of it represented genuine, profound progress in our understanding of the universe's invisible architecture. But the map also sharpened the original problem, rather than dissolving it. We can now see the cosmic web in its finest detail. We can trace the dark matter filaments. We can identify the nodes where matter clusters. We can watch dark matter and ordinary matter growing together across cosmic time. And what we find when we look at the earliest epochs the map can reach is a web that was already more developed, already more structured and more richly organized than the standard timeline suggests it should have been. The scaffolding was in place before the models said the construction company had arrived. This points towards something deeper in the first chapters of cosmic history, something that seeded the structure that gave dark matter its initial push, that accelerated the assembly of the web before any star had lit the darkness, and the one candidate that keeps appearing at the very foundation of every theory about early seeding, an object so strange, so extreme, so deeply embedded in the earliest physics of the universe that it may have shaped the skeleton of everything that followed, is something we have spent decades trying to understand. The kind of object that does not emit light, that bends time, that swallows everything that reaches it, and Webb found them far earlier in the universe than anyone believed was possible. Roberto Maiolino was reading his own data wrong. That was the only reasonable explanation. A black hole of several million solar masses, parked at the center of a galaxy that had no business being that old, that far back in time. He checked again, then he said, "It is essentially not possible. There is a rule in black hole physics, a limit, a ceiling on how fast even the most voracious black hole in the universe can grow. Beyond that limit, the physics becomes self-defeating. The black hole feeds so rapidly that the radiation pouring out of the surrounding gas begins to push new material away, starving the very process trying to feed it. Nature, it seemed, had built a governor into black holes, a cap on ambition." Webb dismantled that assumption in the very first year of its observations, not with one discovery, with many, and each one pushed the timeline further back. Each one planted a more massive black hole at an earlier moment. Each one raised the same impossible question: how does the universe build something this heavy in so little time? Before we can understand why these early discoveries were so disorienting, we need to hold clearly in mind what a supermassive black hole actually is, and how, under ordinary circumstances, one is supposed to form. A supermassive black hole is not simply a large black hole. The term describes a specific class of object. Black holes containing anywhere from millions to tens of billions of times the mass of our Sun, almost always found at the centers of large galaxies. Our own Milky Way has one, Sagittarius A star, with a mass of roughly 4 million solar masses. The galaxy M87 hosts a black hole of approximately 6.5 billion solar masses. These objects are the gravitational engines at the hearts of galaxies, shaping their rotation, their gas flows, and in some cases, their entire fate. Standard astrophysics says these objects grow gradually. A stellar black hole, formed when a massive star collapses at the end of its life, starts with a mass somewhere between 5 and perhaps 100 solar masses. From there, it must feed, slowly, relentlessly, consuming surrounding gas and dust, occasionally merging with other black holes, building mass over timescales of hundreds of millions to billions of years. Picture a city that begins as a single farmhouse. Over centuries, the farm becomes a village. The village becomes a town. The town accumulates commerce and industry and eventually becomes a metropolitan center. That process, slow, iterative, dependent on time, is how supermassive black holes were understood to form. Every step requires the one before it. Reaching millions of solar masses through this process requires an enormous stretch of cosmic time. The universe is 13.8 billion years old. Those billions of years gave our galaxy's central black hole the time it needed to reach its current size. Now imagine finding a fully formed metropolis, a city the size of present-day New York, built on an empty meadow, completed less than 3% of the way through that timeline. Not a village, a city, fully built, fully operational, before the rules of urban development say there was enough time to lay the foundations. That is what Webb found in the galaxy GN-Z11. GN-Z11 had been known to astronomers for years, one of the earliest galaxies Hubble ever detected, and it was always puzzling. Too bright, too luminous for its apparent size, roughly 100 times smaller than the Milky Way, yet shining with an intensity that seemed to require an impractical density of young, burning stars packed into an impossibly compact volume. When Roberto Maiolino at the University of Cambridge and his colleagues turned Webb's near-infrared spectrograph toward GN-Z11, splitting its light into its component wavelengths, reading the chemical fingerprints embedded within, they found something that rewrote the explanation for all that. Brightness. The light was not pouring from stars. The light was pouring from an accretion disk, a churning, superheated spiral of gas swirling inward toward a black hole at the galaxy's center. An accretion disk works like a bathtub drain in slow motion, matter spiraling inevitably inward, compressing and heating as it goes, releasing colossal energy as friction. The closer the gas gets to the point of no return, the hotter and brighter it glows. In the most active black holes, this disk can outshine the entire galaxy surrounding it, hundreds of billions of stars, with the light of a single, concentrated gravitational whirlpool. And in GN-Z11, this was precisely what was happening. The accretion disk was spinning around a black hole of roughly 2 million solar masses, consuming matter at approximately 5 times the theoretical limit for sustainable feeding, 5 times the Eddington rate. The Eddington rate, the ceiling physicists had assumed for how fast a black hole could feed, works like a fire that can only consume as much oxygen as is available before the heat drives away its own fuel. Feed the fire faster than the oxygen can flow, and the expanding heat repels the very air keeping the fire alive. For a black hole, the equivalent process was supposed to set an absolute cap. Above the Eddington rate, radiation pressure from the feeding process should push incoming gas away, shutting off the supply. The feeding should self-limit. GN-Z11's black hole was feeding at 5 times that limit, consuming the equivalent of an entire sun every 5 years. The governor was not working, or the universe in those earliest conditions had never needed one. Maiolino's team published their findings in Nature in January 2024. The title was precise: A Small and Vigorous Black Hole in the Early Universe. But privately, Maiolino described what it meant in more direct terms. It is essentially not possible to grow such a massive black hole so fast, so early in the universe, he said. According to classical theories, there is simply not enough time. John Reagan, a cosmologist at Maynooth University, put it in a way that required no equations. It is like seeing a family walking down the street, he said, with 2 6-foot teenagers, and alongside them a 6-foot-tall toddler. How did the toddler get so tall? The toddler is not supposed to be that tall yet, but GN-Z11 was not alone in the family. Priyamvada Natarajan at Yale University led a separate team that found a supermassive black hole inside a galaxy called UHZ1 at 470 million years after the Big Bang, containing approximately 10 million solar masses. 10 million. In a galaxy so young, the first generation of massive stars may have barely finished forming. The data pointed toward a specific and controversial explanation. This was not a black hole that had grown slowly from a stellar remnant. This object was almost certainly born big, formed through the direct, wholesale gravitational collapse of an enormous pristine cloud of primordial gas that bypassed stellar evolution entirely and became a black hole of millions of solar masses in one catastrophic event. Think of it this way: the gradual route to a supermassive black hole is like building a skyscraper floor by floor over decades. The direct collapse route is more like a landslide, the whole hillside, all at once, collapsing under its own weight into the valley below. No floors laid one by one, just mass, gravity, and the sudden, total surrender of an enormous gas cloud to the point of no return. That mechanism, which Natarajan and her colleagues had theorized for years, received its strongest observational support from UHZ1. And then came the black hole merger detected at 740 million years after the Big Bang. 2 galaxies, and their black holes in the act of colliding, captured by Hannah Ubler's team at Cambridge and published in a Monthly Notices of the Royal Astronomical Society in May 2024. One of those black holes already carried 50 million solar masses. Before Webb, theorists had built 2 scaffolded explanations for how supermassive black holes could reach extreme masses so early: light seeds and heavy seeds. The light seed theory said black holes began as stellar remnants, small and manageable, perhaps 100 to 1,000 solar masses, and grew through sustained feeding and mergers. This was the conventional path. It was like a savings account that compounds over time. Start small, reinvest consistently, and given enough years, the total grows impressive. But here is the problem. For a light seed to reach millions of solar masses by 400 million years after the Big Bang, that savings account would need to compound at the maximum possible rate, not just often, but continuously, without a single missed interval from the very moment of its opening. Every pause, every disruption, every period of insufficient gas supply, any interruption at all, and the math fails. The account doesn't reach its target in time. Even in the gas-rich early universe, where early galaxies were, as Maiolino described, like a buffet for black holes, maintaining that feeding rate continuously for hundreds of millions of years strains what the physics allows. The heavy seed theory, the landslide mechanism, offered a more plausible head start, but it requires very specific primordial conditions, enormous, pristine gas clouds that resist fragmenting into individual stars and instead collapse as a whole. Those conditions may have existed, but they are not straightforwardly built into the standard model, and the frequency with which they would occur remains contested. Neither theory comfortably absorbs everything Webb has found. Both require something unusual in the earliest universe, and unusualness when it appears this consistently across this many independent observations starts to look less like an exception and more like a signal. Beneath both theories lies a far older candidate that has lurked at the edges of cosmological thinking since the 1970s. Primordial black holes that did not form from any star, not from any galaxy, not from any direct collapse of a gas cloud in the first few 100 million years, but from the raw physics of the universe itself, from the extreme density fluctuations that existed in the first fractions of a second after the Big Bang, before any atom had cooled into existence. The idea is physically coherent. In the extraordinarily dense, turbulent conditions of the very early universe, pockets of matter may have been compressed tightly enough by chance fluctuations to tip over the gravitational threshold and collapse into black holes directly. Think of water suddenly freezing into ice in a specific spot while the rest of the lake remains liquid. The same substance, the same rules, but a localized concentration intense enough to trigger a phase change. In the primordial plasma of the earliest cosmos, certain regions may have been dense enough to undergo that kind of immediate gravitational phase change. The result would be black holes that predate every star, every galaxy, every other structure in the observable universe. These objects remain hypothetical. No primordial black hole has been directly confirmed, but research published in Astronomy and Astrophysics in 2024 showed something remarkable. Even a very small population of primordial black holes, constituting less than 1% of the total dark matter, could dramatically accelerate the formation of early structures. They would act as gravitational anchors embedded in the cosmic web before anything else existed, drawing dark matter toward them, seeding the formation of halos, triggering the earliest episodes of star formation around them, effectively behaving as foundation stones, planted before anyone had drawn up the blueprints for the building. If even a small fraction of the dark matter web was seeded this way, not by the slow gravitational accumulation of ordinary matter, but by these pre-stellar gravitational anchors already embedded in the cosmos from its very first moments, then the accelerated structure formation Webb keeps finding would have a plausible explanation. Not impossible physics, ancient geometry, a head start that was baked in before the universe had its first thought. But this remains genuinely uncertain. It may be the right answer, it may be a partial answer, and it may be wrong entirely. We do not know. There is one more dimension to this picture, and it transforms the meaning of everything we have described. The early supermassive black holes Webb has detected were not passive. They were feeding furiously, and that feeding had consequences for the galaxies surrounding them. At the rate these black holes were consuming gas, they were generating outflows, ultra-fast winds of particles driven by the energy released as matter spiraled inward. Those winds swept through the host galaxies, pushing gas outward, disrupting the cold clouds from which new stars would have formed. Picture a river delta. Water flows in from upstream, deposits sediment, and builds land. Now imagine that the pressure of the water flowing through the delta has grown so intense that it begins to erode the delta itself, pushing the sediment back out to sea faster than new land can form. Eventually, the very process that was building becomes the process that destroys. The delta cannot sustain itself. That is what the early black holes appear to have been doing to their host galaxies. The black hole draws matter in, grows rapidly, but in growing generates radiation and winds powerful enough to strip the galaxy of the gas it needed to keep forming stars. In GN-Z11, Maiolino's team found evidence of exactly this process: ultra-fast outflows, carrying gas away from the galaxy at speeds of between 800 and 1,000 kilometers per second, about 2,500 times faster than a commercial airliner. Gas that would have become stars was being expelled instead. A black hole that eats too fast starves its own galaxy, and then, having destroyed its food supply, begins to starve itself. The feeding frenzy carries within it the seeds of its own ending. This interplay between early black holes, the galaxies they inhabit, and the dark matter web that supports both, is a fundamental process of cosmic coevolution, one that Webb is now allowing us to observe directly at an epoch so early in cosmic history that none of our models had fully anticipated what we would find. Stand back from everything we have now assembled, the impossible early galaxies, the dark matter map resolving into finer and finer filaments, the black holes too massive and too early, feeding beyond their theoretical limits, possibly, seeded by objects that predate the first light in the universe. A pattern has emerged, and the pattern is not disorder. The pattern is this: the universe assembled its complexity far earlier, far more efficiently, and through mechanisms far more intricate than our best models predicted. All of these questions about early galaxies, about black holes, about dark matter seeds, about the invisible skeleton holding everything in place, point back toward the same underlying problem. The problem of what the universe looks like at its grandest scales. How the model that has described it so successfully for decades is holding up against data from epochs it could never previously see. That question does not live at the level of individual galaxies or individual black holes. It lives at the level of the cosmological model itself, at the level where fundamental tensions accumulate, where the expansion rate of the universe is measured, where the predictions of our best theories and the evidence arriving from the most distant observable light either converge or increasingly do not. And Webb has something to say about that too. At some point in every scientific revolution, there comes a moment where the numbers simply refuse to agree. The instruments are working, the calculations are correct, everything was done properly, and yet the two answers, each earned through decades of careful work, point in different directions. That moment in modern cosmology arrived some time ago, and Webb has made it impossible to look away. Science is not in the business of certainty. Scientists are often the first to say that. What science produces is not truth written in stone, but the best currently available description of reality, a description that must always remain open to correction if the evidence demands it. The ΛCDM model, the standard model of cosmology, the framework that has successfully described the large-scale structure and evolution of the universe for decades, produced extraordinary results, extraordinary precision. Predictions about the geometry of space confirmed to fractions of a percent. Predictions about the amounts of dark matter and dark energy that matched independent measurement after independent measurement. A framework so robust it began to feel, in many corners of the field, like a settled matter. And then Webb arrived, and the model, subjected for the first time to observations at the true edge of cosmic time, began to show something that had been building quietly for years. Not a collapse, not a sudden failure. Something subtler, and in some ways more profound. a crack in a structure that had looked flawless. To understand what the tensions mean, we need to first appreciate what the standard model of cosmology actually does, and why its success for so long was so remarkable. The ΛCDM model, lambda for dark energy, CDM for cold dark matter, is not a single equation or a simple idea. It is a framework, a comprehensive description of how the universe began, how it expanded, how matter clustered under gravity over billions of years, how the first structures formed, and what the geometry of space itself looks like on the largest scales. Every ingredient in the model was determined by real measurements: the age of the universe from the cosmic microwave background, the density of dark matter from galaxy rotation curves and gravitational lensing, the density of dark energy from the accelerating expansion confirmed in 1998 by observations of distant supernovae, work that earned Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize in Physics in 2011. Think of the standard model as a master recipe that cosmologists refined over decades. The recipe specifies precise quantities for every ingredient: dark matter, dark energy, ordinary matter, the initial density fluctuations, the expansion history, and uses those quantities to predict, with mathematical precision, what the universe should look like at any given moment in its history. And for a remarkably long time, every test of that recipe produced a cake that matched exactly what was expected. But a recipe that works perfectly in every test kitchen eventually meets a kitchen it was never designed for. The earliest observable universe, the cosmic dawn that Webb was built to illuminate, was precisely that kitchen. And when the recipe's predictions were placed beside Webb's observations, the discrepancies that had been quietly accumulating for years became impossible to dismiss. The most direct tension has already unfolded across everything we have established together. Galaxies appearing too early, too massive, too chemically evolved. Black holes too large and too active in too little time. An early dark matter web that appears more developed than the standard timeline allows. Each observation individually admits possible explanations, but taken together across dozens of independent data sets, confirmed by spectroscopy, analyzed by teams from multiple continents working independently, a pattern emerges that no single adjustment to the recipe can easily resolve. The ΛCDM model predicted that the early universe would be populated by small, disorganized, gas-dominated proto-galaxies, fragmentary, primitive, seeds, not trees. Webb found trees, fully formed, structurally organized, chemically enriched galaxies existing at moments when the model said only seeds should have been germinating. Scientists on both sides of this debate are genuinely rigorous people doing genuinely careful work. Some argue that measurement uncertainties in how we estimate the masses and ages of early galaxies remain large enough to absorb the discrepancy, that the trees Webb is finding, when examined more carefully, may prove to be younger or lighter than they appear. Others argue that spectroscopic confirmation, which provides the most direct, least ambiguous measurement of a galaxy's distance and chemical state, has now placed enough of these objects on secure observational ground that the uncertainty defense no longer fully holds. The tension is real. Its magnitude and its cause remain unresolved. But of all the cracks in the standard model that Webb has sharpened, one stands apart, because it does not involve early galaxies at extreme distances. It involves a number, a single, fundamental number that describes the most basic property of the universe we live in today: how fast space itself is expanding. That number is the Hubble constant. The Hubble constant is a measure of the expansion rate of the universe at the present moment. It tells astronomers, for any 2 points in space, how quickly those points are being carried apart by the expansion of space itself. Every measurement in cosmology, every distance, every age calculation, every estimate of how the universe will evolve in the future depends on getting this number right. And for decades, 2 independent methods of measuring it kept producing different answers. Here is how each method works. The first starts close and builds outward, what astronomers call the cosmic distance ladder. You begin by measuring the distances to nearby pulsating stars called Cepheid variables, whose brightness-to-period relationship was first discovered by astronomer Henrietta Swan-Leavitt in 1908. Those Cepheid distances calibrate your first rung. From there, you measure the distances to galaxies containing both Cepheids and a specific type of exploding star, a Type 1a supernova, whose peak brightness is reliably standardizable. That gives you the second rung. Those supernovae then carry you out to distances of billions of light years, where you can measure how fast the universe is actually expanding today. The result, produced by the SH0ES team, led by Nobel laureate Adam Rees at Johns Hopkins University, yields a Hubble constant of approximately 73 kilometers per second per megaparsec. Every megaparsec, every 3.25 million light years, of space is expanding at 73 kilometers per second. The second method starts at the opposite end of time. The Planck satellite's map of the cosmic microwave background, the oldest light in existence, contains acoustic patterns embedded in the universe's first light. Those patterns encode the initial conditions of the cosmos with extraordinary precision. Plug those initial conditions into the best available model of cosmic evolution and project forward 13.8 billion years, and you get a prediction for what the Hubble constant should be today. The Planck team's result is approximately 67.4 kilometers per second per megaparsec. 67 versus 73, those numbers might look close. But the difference is not just a number, it is a gulf. In statistics, a 2 sigma discrepancy is considered interesting. A 3 sigma discrepancy gets people's attention. A 5 sigma discrepancy, the level at which physicists typically declare a discovery in particle physics, means the probability of the gap occurring by chance is less than 1 in 3.5 million. The Hubble tension, as of 2024, stands at approximately 5 sigma. Not a rounding error, not a systematic quirk. A statistically devastating disagreement between two of the most precisely measured numbers in the history of science. And here is where the story fractures most sharply, because the obvious explanation that one of the measurements must simply be wrong has now been eliminated by Webb itself. When Webb launched, many astronomers held a quiet hope. The most likely culprit for the tension, they reasoned, was a subtle error in the first rung of the cosmic distance ladder, the Cepheid measurements, crowding contamination, the possibility that overlapping starlight in distant galaxies was systematically inflating or deflating the brightness measurements of those pulsating stars, throwing off every step that followed. Webb's sharper infrared vision would, they believed, resolve those stars cleanly and either confirm or correct the problem. Adam Rees's SH0ES team used Webb to observe more than 1,000 Cepheid variables across 5 galaxies containing 8 Type 1a supernovae, spanning the full range of distances previously measured with Hubble. The results were published in the Astrophysical Journal Letters in February 2024. Webb's measurements agreed with Hubble's, not approximately, precisely. The formal difference between the two instruments' distance determinations was less than 1%, well within the margin of noise, with measurement errors negated, Rees said in the NASA statement accompanying the results. What remains is the real and exciting possibility that we have misunderstood the universe. The escape hatch had been closed. The measurement was not wrong. The discrepancy was real. Rees described the situation in a way that deserves to be heard clearly. Imagine, he said, that you have set an anchor on one shoreline of a very wide river. On the opposite shore, someone else has set a separate anchor. Both anchors are firmly placed. Both are precisely measured. But when you measure the river between them, the two anchors appear to be on shores that are further apart than they should be, based on everything you know about how wide rivers grow. You cannot see the middle of the river. You cannot directly observe how the universe's expansion rate was changing in the billions of years between the earliest measurements and today. And somewhere in that invisible middle stretch, something is not behaving as the model predicts. Within the astrophysics community, this question has generated genuine and unresolved debate, not performative controversy, real, professional, rigorous disagreement between careful scientists who respect each other's work. On one side stands the position that the Hubble tension may still reflect a systematic error, not in Hubble's Cepheid measurements, which Webb has now validated, but in other steps of the distance ladder, or in the assumptions baked into the CMB-based prediction. Wendy Friedman's team at the University of Chicago, using Webb data and 3 entirely independent distance measuring techniques, the tip of the red giant branch, carbon-rich giant stars, and Cepheid variables, published results in 2024 suggesting that the tension may be smaller than Rees's team finds. Their measurement falls between the two camps. Friedman stated directly, "Based on these new Webb data and using 3 independent methods, we do not find strong evidence for a Hubble tension." The debate continues. On the other side stands the position that the tension is large enough, confirmed by enough independent methods, and persistent enough across enough different observations, that it points beyond measurement error toward genuinely new physics. Something, this view holds, is either different about the early universe than the standard model allows, perhaps an early form of dark energy that temporarily sped up expansion before the Big Bang's first light was emitted, or something about dark energy's behavior across cosmic time that the ΛCDM framework has not fully captured. Neither side has produced a smoking gun. Neither side has been proven wrong. This is not failure. This is science working exactly as it should, grinding through disagreement toward resolution that only more data can provide. We began this journey by asking what the shape of the universe means. We established that geometry, the flatness confirmed by Planck and WMAP to within 0.4%, describes the large-scale architecture of space, and we noted that geometry alone is not the full answer. The web of structure inside that geometry is equally fundamental, but now a third dimension of meaning has emerged. The shape of the universe is not only its geometry, not only its structural architecture. The shape of the universe is also its history, the specific trajectory by which space expanded from the Big Bang to the present moment. And if that expansion history is not what the standard model predicts, if the universe expanded faster in some early epoch, or if dark energy has been behaving differently than the cosmological constant assumes, or if some physics we have not yet identified was active in the first few 100,000 years, then the shape of cosmic time itself is different from the shape we drew in our best models. The Hubble tension, in this sense, is not a measurement problem. It is a shape problem, a problem about the path space took from there to here, and the fact that Webb, by confirming the distance measurements, eliminating the easy escape routes, and simultaneously revealing early galaxies and black holes that challenge the standard timeline, has converged multiple independent tensions into a single sharpening crisis, is the most important scientific development in cosmology in at least a generation. Think of the standard model as a map that successfully described every road you had ever traveled, a map so reliable and so thoroughly tested that you had stopped questioning it, and then one day you reach a road the map says should turn right, and the road turns left. You check your instruments. They are working. You check the map. The map was based on all the right data, and yet the road turns left. The question is no longer whether something is wrong with the map. The question is how deep the error goes, whether the road you are on is a small, unlabeled detour, or whether it leads somewhere the map was never designed to take you. What we now possess, after traveling through the geometry of space, through the first light of the universe, through impossible early galaxies and invisible dark matter webs and black holes feeding beyond the limits of physics, is a picture of the universe that is simultaneously more confirmed and more contested than it has ever been. Confirmed because Webb has given us the most precise observations ever made of the earliest cosmic epochs. Contested because those observations, measured against the most successful model in the history of cosmology, keep revealing discrepancies that do not quietly resolve. We know the universe is flat. We know the cosmic web is real and mapped. We know structure appeared earlier than expected. We know the expansion rate measured close to us and the expansion rate predicted from the beginning of time do not agree, and Webb has ruled out the instruments being wrong. What remains then is not a technical problem waiting for a better calibration. What remains is the possibility, taken seriously now by the most careful minds in the field, that something fundamental about our understanding of the universe is incomplete. And here, at last, we can ask the question the entire journey has been building toward. Not the shape of space, not the structure of matter, but the deepest question of all, the one that stands behind every tension, every anomaly, every galaxy that should not exist, and every black hole that grew too fast, and every measurement that refuses to agree. What is the universe truly? And what does it mean that we, small, brief, entirely improbable, are the thing inside it that built instruments precise enough to notice the cracks? That question deserves its own moment, one final, unhurried conversation, and that is exactly where we are going. We started with a question about shape. It seemed at first like an abstract problem, the geometry of something too large to touch, too old to imagine. But somewhere along the way, without quite noticing, the question changed. The universe's shape turned out to be our story too. We have been travelling together through an unusual kind of dark, not frightening dark, the dark of a clear night when your eyes have finally adjusted, when the sky fills with more detail than you expected, more depth than the map suggested, more structure in the emptiness than anything you were told to look for. What we found, by following Webb's golden eye into the earliest light the universe ever released, was not the simple, elegant, well-behaved cosmos our best models had drawn. We found something older than predicted, and more intricate than imagined. We found structure that should not have been finished, in a time frame too short to finish it. We found invisible scaffolding mapped in unprecedented detail, tracing the exact places where every galaxy we have ever seen was destined to gather before a single star had lit the darkness. We found the expansion rate of space itself in disagreement with its own origin story, a discrepancy that Webb confirmed was real and left unresolved. And now, at the end of all that, a question earned by everything we have travelled through together demands its answer. What does it all mean? Not in the technical sense, in the human sense. What is the true shape of the universe? Let us begin with what we can say with genuine confidence, what the data has delivered so clearly that the scientific community, despite all its productive disagreements, holds this in common. The universe, on its very largest scales, is geometrically flat. Not flat like a table, flat in the precise mathematical sense that parallel lines remain parallel, that the angles of a triangle always sum to exactly 180 degrees, that light, travelling in a straight line, never curves back. This was confirmed by the Planck satellite to within 0.4%, a precision so fine that if you built a perfectly flat floor stretching from one end of a continent to the other and could detect any deviation in height smaller than a single sheet of paper above the baseline, you would still be working at a coarser tolerance than the universe's measured geometry. Space, on the grandest scales we can probe, obeys the simplest set of geometric rules. That flatness has a profound consequence. The universe may well be infinite, not bounded, not curved back on itself like a sphere, open and extending outward without limit in every direction, following flat geometry into a darkness that, by definition, has no far wall. We live, to the best of our current knowledge, in an infinite flat space. But the flat geometry is only the first sentence of what Webb revealed, and the rest of the story is far stranger, far richer, and far less settled than that clean first line suggests. Inside the flat geometry lives a structure, a vast three-dimensional architecture of matter arranged not randomly, not uniformly, but in the pattern of an immense web. Filaments of dark matter and gas stretching hundreds of millions of light years, intersecting at nodes where galaxy clusters numbering in the thousands have assembled, enclosing between their threads enormous hollow voids of near emptiness. The cosmic web, that invisible skeleton running through the universe, has now been mapped by Webb at the highest resolution ever achieved in human history. Its dark matter threads confirmed in a side-by-side comparison that made scientists applaud in a conference room to be finer, sharper, and more richly detailed than 3 decades of prior observation had managed to show. And inside that web, woven into the threads at every scale, galaxies appeared earlier than they should have, more massive than the models allowed, more chemically evolved than the timeline permitted. Black holes fed beyond their theoretical limits. The thread that carries the universe's structure was assembled faster, more efficiently, and in a manner still not fully explained. We know what the universe looks like. We do not yet fully understand how it became that way, or why, or what the disagreements between our measurements are trying to tell us about physics we have not yet discovered. Both of those things are true at once. The clarity and the mystery coexist. Step back now from the specific discoveries and look at the full picture. We asked what the shape of the universe means. We found that it means at least 3 different, deeply connected things. First, the geometry of space itself. Flat, confirmed, understood with precision. Second, the physical structure of matter within that space. The cosmic web, the dark matter skeleton, the filaments and nodes and voids that organize visible matter into its current arrangement, mapped, still being refined, deeply surprising in its early development. Third, and most quietly profound, the shape of cosmic time, the trajectory from the Big Bang through the first light, through the cosmic dawn, through the assembly of the first galaxies and black holes and the vast architecture of dark matter, that the universe actually took to become what we observe today. And here, the shape is still being measured, still being contested, still yielding surprises. The honest answer to the question, what is the true shape of the universe, is this. It is flat in its geometry, webbed in its structure, and in its history, more richly complicated than we had the instruments to see before now. Webb did not reveal a simpler universe. Webb revealed a more complete one. And completeness, it turns out, means more questions answered and more questions opened, simultaneously. Pause here for a moment, not to absorb another discovery, just to be here. You came to this with curiosity, and you have traveled across 13 billion years of cosmic time, through the geometry of space and the architecture of the invisible, and the mathematics of expansion itself. You have sat with some of the most contested and consequential questions in science, not as a spectator, but as someone genuinely trying to understand. That matters. Curiosity at this scale, sustained across ideas this abstract and this vast, is not a small thing. The universe is not aware that you are watching it, but you are. And in that asymmetry between the indifference of an infinite cosmos and the stubborn, wondering attention of a human mind, something genuinely important lives. The cosmic web spans what is estimated to be the full breadth of the observable universe, roughly 93 billion light-years, or about 55 billion miles across. Our entire solar system, from the Sun to the outermost reaches of the Oort cloud, spans approximately 2 light-years. At the scale of the cosmic web, our solar system is less than a single atom sitting on the surface of a continent, not a grain of sand, not a molecule, an atom. And yet the human mind, assembled from those atoms, housed in a body that can be harmed by rain, built instruments precise enough to detect the way dark matter curves light by fractions of a percent across billions of light-years. Precise enough to read the chemical signature of oxygen in a galaxy that existed 290 million years ago. Precise enough to measure the expansion rate of space to within less than 1%, and then notice that 2 separate measurements, each done with extraordinary care by Nobel laureates, disagree by an amount so small it cannot be detected without instrumentation, and yet so significant it may require new physics to explain. That precision is not a footnote. That precision is the most remarkable fact in this entire story. What does the Hubble tension mean? We do not know. Whether it points to an early form of dark energy that briefly accelerated the universe's expansion before the first light was released, or to something in the behavior of dark matter we have not yet captured, or to physics operating below any scale we have yet probed, we genuinely do not know. The answer is not withheld. It simply has not arrived yet. What seeded the earliest structure? Ordinary quantum fluctuations amplified by cosmic inflation, or primordial black holes born in the first fractions of a second, or some interplay between the two we have not yet disentangled? We do not know. What precisely dark matter is, not what it does, which we have now mapped with extraordinary resolution, but what it actually is at the subatomic level, what particle or field carries its mass and governs its behavior. We do not know. These are not failures. They are the exact shape of where human knowledge currently ends and where the next generation of instruments, the next generation of minds, will begin. Every question we cannot yet answer is an open door. The universe has never run out of things to show us. There is no reason to believe it will start now. We began this journey with a simple image, an invisible thread, the dark matter filament running through the universe, carrying the visible world along its length, deciding where galaxies form and where voids open, organizing the cosmos from its first moments into the vast web we can now map. At the very end of where we started, those words landed quietly. The invisible thread runs through you. And now, having traveled through everything we have traveled through, that sentence means something different, something more. Because the thread was not only the dark matter skeleton threading through space, the thread is also the one running unbroken from the oldest light in the universe, straight through to wherever you are right now. From the quantum fluctuations in the first fraction of a second, through the formation of hydrogen atoms, through the assembly of the first stars, through the deaths of those stars that forged the heavier elements, through the formation of our sun and its planets, through the emergence of life on one of those planets, through the slow, patient, improbable development of a species curious enough to point a golden mirror at the oldest light in existence and ask what it means. That thread is you, and it is continuous, unbroken, stretching all the way back to the beginning. Webb did not discover it. Webb let us see it clearly for the first time at both ends simultaneously. The universe does not care about us. That is not a dark thought. It is simply the truth of the scale, and accepting it honestly is the beginning of something more important than comfort. The universe does not care about us, and we built Webb anyway. We spent 30 years designing it, testing it, folding it into a rocket, launching it into the cold of space, unfolding it piece by piece with 284 single point of failure mechanisms, and then spent years analyzing everything it told us, arguing about what it means, revising our models, building better ones, asking deeper questions, not because we had to, not because survival required it, because we could not stop wondering. The universe is flat, the web is real, the dark thread holds everything in place. The early cosmos was stranger and richer and more complex than we predicted. And somewhere in the middle of all that vastness, in an unremarkable arm of an unremarkable galaxy, in an unremarkable cluster on one of countless filaments in the cosmic web, something happened that the universe may not have anticipated. Something started asking questions about the whole. The shape of the universe turns out to include that. The shape includes the fact that matter, arranged just so, and given enough time, becomes curious about the container it inhabits, builds instruments to see beyond its own limits, discovers that those limits are further than it thought, revises, wonders, begins again. That is not a small addition to the story of cosmic structure. It may, in fact, be the most extraordinary structure of all. The thread was always there, running through the dark matter web, through the ancient filaments, through the first galaxies, through the oldest light, through the atoms forged in the first stars, scattered by their deaths, gathered again by gravity into the world you stand on, the breath in your lungs, the mind that followed this story to its end. We are not separate from the universe. We are a late arrangement of it, one that, against enormous odds, learned to look back. Webb looked back 13.8 billion years, and in that ancient light, stretched, delayed, arriving at last, the universe looked back at itself. That may be everything that matters.